Good evening everyone. Thank you for joining me for this video. Promise you a very useful video here. We know that for an odd function, we have this specific setup for a symmetric interval minus a to a, where numerically these numbers are the same, but they're just differing with regards to their sign. We have an odd function present here, and we're doing a definite integral. The result in terms of that definite procedure is always 0. That is, the net area below and above the curve zeroes out. What are we talking about here? Odd functions. Cubic function is a good example, x cubed. If you look at it from 1 to minus 1, this is like minus a to a. We end up seeing part of the area is below the curve and part is above the curve. If you were to take the area of this, they would zero out, because this would be kind of a negative area. This here would be a positive area. The net area would be 0. And this right here is a very legitimate fact with regards to odd functions. Take something a little bit more difficult in appearance and you can rely on this property to be 100% true for something even as seemingly difficult as this. Hyperbolic tan from minus infinity to positive infinity, minus a to positive a dx. If you were to graph it out, it looks something like a inverse tangent, except the asymptotes here are different. You have a 1 here and a minus 1, and with regards to the asymptotes, horizontal asymptotes, you're looking at a curve which looks like that. Minus infinity would include all of this area, positive infinity, all of this area. The net of these two again will be a 0. Net area would be a 0. That's what we're talking about. Even the fact that you're seeing something like a type 1 improper integral, this function would hold very well true. Keep in mind this specific fact, this right here and this right here, and with regards to this cubic function, which could be written as this, x cubed dx, and these intervals 1 and minus 1, these a and minus a must very well be in the domain of the function you're looking at. This interval must be in the domain. It cannot be like you're looking at some a, positive a or minus a value, which is falling to be some sort of infinite discontinuity or a vertical asymptote. That should not be the case. Minus infinity, positive infinity are in the domain of that. And any of these numbers from minus infinity to positive infinity are in the domain of cubic function. So we have laid out this practical solution for you. Now let's look at this exact question formally. How do you prove it to be the case? How about this? You start like this. You have from minus a to a 0. We're going to split the minus a to an a interval. We should be using the square parentheses, and we're going to insert a 0 in between, which you can. We have an f of x dx. Here we have from 0 to a, f of x dx. We can use a property of intervals and flip this. It's a property of integrals actually, and we can flip the intervals around. We have exactly that. And then we have all of this coming right here. And what I can do over here is use a property of odd functions. What's the property of odd functions? We know that minus f of x is equal to f of minus x. Think about it. This is equal to that in terms of an odd function which is symmetric about the origin. I have something here which looks like a minus f of x right here, and I can convert it into that without affecting the intervals in any way. I can keep 0 and minus a, and I can bring a minus x right in here. You see this? Minus f of x is equal to f of minus x. There it is. That right there is the most key or the most crucial step of all of this. But by doing that, you've ended up with a composite here. You have to do polynomial substitution. U is equal to minus x, du is equal to minus dx, dx is equal to minus du. New intervals, u1 and u2, everything with respect to this. u1 is still a 0, u2 is a minus of a minus a, which is an a. Now what we can do is work right over here with exactly what we have over there. Substitution right over here, and let's do it. We have what will be now a 0 and a, f of u du, and we have a minus du, which will bring right out here. And everything is in place from this substitution. If you look at this specific part right over here in the box, this part right here, and you look at all of this right here, you can literally take this and negate it with this and you're done. You can literally use this expression right here and you're done. You have an f of x positive, and technically you have a minus f of x. You just have u's instead of x's, and this very well crosses out with that, and you really end up getting a 0. But if you don't want to take that convenient shortcut, you can do definite integration and work and keep continuing from here. You'll do the definite integration of this and this. And let's divide everything here. The antiderivative of this is going to be capital F of u, and then you have a and a 0, and then you have the antiderivative of this, which is capital again, and then you're looking at it from a and 0. do the definite integration. You'll have f of a minus f of 0. Here you'll have f of a minus f of 0. Now you can just open this up. You'll have minus f of a plus f of 0. And we'll have plus f of a and minus f of 0. And we're very close to being done here. This positive f of 0 cancels out with this negative. This positive f of a cancels out with this minus f of a. And we're ending up here with 0, which is exactly what we wanted. So the proof has been here and placed before you. It very well required you to bring this in right at this step over here, as I showed you, where the minus f of x became f of minus x, which I erased and modified by means of the substitution technique. But you saw all of that come into play. Remember a very key point here again, this right here should be in the domain of your odd function, and then from there you can proceed. And all of it here is before you. You can watch this as you need, and thank you for watching. Have a nice day.